We have a population of 1,000 spoons. A little bit silly, but the numbers are nice. So that's why I wanted to do this one. These spoons can either be clean or dirty. So I'm going to keep this population of 1,000 spoons. That's going to be constant throughout this problem. And their two states are either clean or dirty. A spoon is going to either be clean or dirty. If it even has a little teeny speck on it, we're going to classify it as dirty. So we're going to begin with 600 clean spoons and 400 dirty spoons. And maybe our unit of time here, we can say it's a shift at a restaurant or whatever. It doesn't really matter what the unit of time is. It's that we're going to have a set number of units of time. There's a 20% chance that a clean spoon will remain clean. Now maybe that means that somewhere during the shift it gets dirty, but it ends the shift clean. 20% chance a clean spoon remains clean. What's going to happen to the rest of these spoons? The only other thing that could happen is that they become dirty. So if there's a 20% chance that a clean spoon remains clean, that means there's an 80% chance that a clean spoon is going to become dirty. Now there's a 60% chance that a dirty spoon remains dirty, or it ends the shift dirty. So that means there's a 40% chance that it'll become clean. So let's take a look at our pieces of information that we need to work with here. We need our initial state vector, the vector that tells how the system begins. Now I'm using this subscript right here to represent what unit of time we're on. So if we're talking about the beginning of the shift, beginning of the problem, we're dealing with time as 0, or the number of units of time is 0. And I'm going to put the clean spoons on top. So I'm putting 600 on top, 400 on the bottom. I need to be consistent all the way through. So if I'm going to put clean on top in my initial state vector, I need to put clean on top in my transition matrix. Now that transition matrix, which I just call A, not exciting, but it works, I'm going to put what it's going from and what it's going to. So here's what I'm talking about. We said that there's a 20% chance that a clean spoon remains clean. That means it's going from being clean to being clean. That was 20%. Then 80% go from being clean to being dirty. Notice how that column adds up to 1. That's really important with a Markov chain. If it's really a Markov chain, our columns should add up to 1 because everything has to be accounted for. So all the clean spoons are now accounted for. 100% go somewhere. Now let's say that I go from being dirty to being clean. What percent do we say that was going to be? If 60% remain dirty, they're going from being dirty to being dirty. From dirty to dirty. But what percent go from dirty to clean? That was 0.4. So this is our transition matrix. We've got our two pieces of information we needed to start. Let's go ahead and see what happens after the first shift. I'm going to denote that as x sub 1. X sub 1 is the state after 1 unit of time. And that's going to equal our transition matrix A times our x sub 0, which in this case is the row 0.2, 0.4, second row is 0.8, 0.6 times my initial state vector 600, and in the second row 400. Now if you remember, when you multiply matrices, you do a row times a column. Maybe you don't need to make the circles, but I do. It keeps me from making mistakes, so I'm not embarrassed about it. 0.2 times 600 plus 0.4 times 400. That's what's going to be in the top row. Then in the second row, I'm going to have 0.8 times 600 plus 0.6 times 400. Now if I work that out, let me consult my little paper here, I get 280, 720. So I began with 600 clean, 400 dirty. Now I have 280 clean, 720 dirty. Let's see what would happen after the second shift. If I wanted to figure out x sub 2, which is after the second shift, I would do that again. I would just multiply my 0.2, 0.4, and in the second row 0.8, 0.6. But now I multiply it times x sub 1. I multiply it by the 280, 720. And that's going to give me an answer of 344, 656. So this was clean on top and dirty on the bottom. Now if you'll notice, this 280, 720, that really came from a times x sub 0, right? So this x sub 2 is really a times, now this was x sub 1, right? If I write out that x sub 1 was really a times x sub 0, I get that really x sub 2 was just a squared times x sub 0. And I could continue that on. I could figure out x sub 3. I could multiply a times my x sub 2 that I had. I could multiply that out and get $331.2 clean, 668.8 dirty. And again, if you notice, that was really a times my x sub 2, right? But then x sub 2 was actually a times x sub 1, but then x sub 1 was actually a times x sub 0. So in other words, x sub 3 is really a cubed x sub 0. We could continue that process on. If I needed to know, for example, x sub 956, I don't know why you'd need to know that, but if you did, you could say it would be a to the 956th power times x sub 0. So we're hoping if we really have to calculate a to the 956, that we have some really powerful software, something like MATLAB or Mathematica or whatever. Now, if you're not allowed to use that kind of software, there is a way around that, using eigenvectors and eigenvalues. And that's what we're going to look at in a few minutes. Suppose we have a population of birds which inhabit 3 islands, X, Y, and Z. Really general names there. Birds fly back and forth among the 3 islands, and we are going to have a constant population because we're not going to let the birds fly off into the ocean or anything. We're going to keep them there on those 3 islands. The daily process is the birds on island X, 20% stay on X, 50% fly to Y, 30% fly to Z. Notice the 20, the 50, the 30 add up to 100%. Birds on island Y, 20% stay on Y, 40% fly to Z, 40% fly to X. And then the birds on island Z, 20% stay on Z, 30% fly to X, 50% fly to Y. Okay, so we have a constant population, and then there are 3 states that these birds can take on. They're either on X, Y, or Z. Our unit of time is a day. Not that it really matters, it's just some unit of time. And so we have a Markov chain situation here. Let's summarize this information to get our transition matrix. Okay, so the ones that are flying from X to X, are 20%. The ones that fly from X to Y, is 50%. And from X to Z, 30%. Okay, from Y to Y is 20%, that's here. From Y to Z is 40%, it's on the bottom row. And then 40% fly to X, that's 0.4 up here because they go from Y to X. And last, the ones on Z, 20% stay on Z, 30% fly to X, 50% fly to Y. So that gives us a summary. It also gives us our transition matrix. So that's our A matrix. So I'm going to erase all this information about what they're doing. Okay, so our A matrix, our transition matrix, point 2, 0.4, 0.3 across the top row, 0.5, 0.2, 0.5 across the second row, 0.3, 0.4, 0.2 across the third row. And so you'll notice again, every column adds up to 1 because all the birds that were on island X had to go somewhere. They either stayed on X, went to Y, or went to Z. So every column adds up to 1. Now I also need, and I didn't tell you this, what the initial state vector is. I need the initial state vector. So I'm just coming up with this out of the clear blue sky. Let's say this was given in this problem. And we actually begin with 400 birds on X, 300 birds on Y, and 800 birds on Z. Now it's pretty easy to keep these in order because I had them arranged alphabetically. But do notice that I began with my X on the top row and I have the X on the top row of my initial state vector. So this was given in this problem. I didn't write it down earlier. And you'll notice that I have a constant population of 1,500 birds. So throughout this process, as we work on this problem, I'll always have 1,500 birds. So let's see what's going to happen after 1 day. Now remember, we notate that as x sub 1, and that's going to be our A times our x sub 0, which is this 0.2, 0.4, 0.3, second row 0.5, 0.2, 0.5, third row 0.3, 0.4, 0.2. I'll multiply that by 400 in the first row, 300 in the second row, 800 in the third row. I get 440. Now that's going to be 440 birds on X, 660 on Y, and 400 on Z. And if I add that up again, you'll see again you still get 1,500 birds. Okay, if I wanted to figure out for 2 days, we're looking for X sub 2, which I can again just multiply this transition matrix times the answer I just got. And I'll find out that at the end of 2 days, I have 472 birds on X, 552 birds on Y, and 476 birds on Z. If you continue this process and you get X sub 3, which would be after 3 days, you could, again, multiply your 0.2, 0.4, 0.3, 0.5, 0.2, 0.5, 0.3, 0.4, 0.2 by what I just got, 472, 552 in the second row, 476 in the third row. And I'll find out that after 3 days, I have 458 on X, 584.4 on Y, and 457.6 on Z. Now maybe we're dealing with units that are actually millions or something. You know, I probably don't have 0.4 of a bird. It's just an illustration. You know, 0.4 of a bird probably couldn't fly. But you can see how I could continue this process on if we needed 10 days, 15 days, 100 days. We could continue on with this process. If I did need to do something huge, though, like 100, there is a process using, as I mentioned, eigenvalues and eigenvectors, which I'll derive in a second. And that's what we're going to do instead of actually doing this 100 times. Okay, so we're going to be trying to calculate the steady state vector. Over time, this system is going to head to what we call a steady state, the state of the system after a long period of time. So we're going to have kind of a set place where this is heading over a long period. If I, for example, needed to calculate x sub n, where n is some huge number, I don't want to have to be multiplying that A matrix over and over and over again, nor do I want to have to, by hand, raise it to a huge power. So what I'm going to do instead is come up with a plan. So we know that x sub n is a sub n times our initial state vector. Well, if I had some clever way of writing that initial state vector, maybe using an eigenvector or two, or however many I have. For example, if I do it this way, now I might have more eigenvectors than that, but let's just say I'm dealing with a system that only has 3 eigenvectors. So this is where the C sub whatevers, C1, C2, C3 are constants. And the U1, U2, and U3 are eigenvectors. If I can write that initial state vector as a combination, this is called a linear combination of the eigenvectors, then I can actually substitute this here into that equation. Now that might seem like it's going to make it look worse, and it will initially, But then if you look at some substitutions we can make, it's going to be really cool. It'll get us into a good position. Okay, so let's do that. Let's say I have x sub n. We said that's a to the n times x sub 0. But in place of x sub 0, I'm going to write c1u1 plus c2u2 plus c3u3. Okay, now let's distribute the a to the n power. So, and remember, I have a property that says if I have a number, a constant, times a matrix, times a vector or another matrix, I can slide that constant wherever I want to. So I could actually write this as c sub 1 a to the n u sub 1 plus, distributing the a to the n over to the next one, I could write it as c sub 2 a to the n u sub 2 plus c sub 3 a to the n u sub 3. So I've distributed a to the n to each of those vectors times a constant. Now the beautiful part. You ready? Using the definition, if you remember the definition AU equals lambda u, that was where these u's are eigenvectors, and this lambda right here was the eigenvalue corresponding. Oops. So what we did in the previous section was we were given A, which was a matrix. We calculated the eigenvalues, and then based on the eigenvalues, we got the eigenvectors. And what I'm saying is we've got the eigenvectors, and to each one of these eigenvectors, there's a corresponding eigenvalue. So, for example, lambda 1 is the eigenvalue corresponding to u1, the eigenvector, and so on. Well, in each case, I can say that A times U is lambda times U. In other words, in every one of these places down here, for example, this A to the n U1, this A to the n U2, and this A to the n U3, I can replace the A and the U part, I can replace the A with the corresponding lambda. Now, why is that special? Well, A is a big old matrix. What is lambda? Just a constant. Oops. So in place of this big old matrix that I had to raise to a power, which we already decided we didn't want to have to do, I can just raise a constant to a power. It's not that difficult, right? We can take any calculator and pretty much go, you know, if I had like 0.5 or something, I can go 0.5 to the 100th power, and it's not a big deal. It gives me an answer almost immediately. So I replaced this big matrix to a huge power that I didn't want to do with a number to a power. Not very difficult. And you're going to find out that with a Markov chain, there's actually a theorem, which we don't really cover in this class, but it's true. There's always going to be one of these eigenvalues that's 1, the number 1. Every other eigenvalue is going to be between -1 and +1, not including -1 and +1. So you'll have numbers like 0.3, 0.2, -0.5 as your eigenvalues. But then you'll have one of these guys that's the number 1. And that's going to be really special, which you'll find out in the next example. So back in our first example, we had 1,000 spoons. 600 were clean, 400 were dirty, and that was our initial state vector. Our transition matrix, first row was 0.2, 0.4, second row was 0.8, 0.6. If we wanted to find the state of the system after 100 units of time, maybe it's 100 shifts, that's x sub 100. We don't want to have to calculate a to the 100th power times x sub 0. So instead I'm going to use the steady state vector. And the way that's going to work is, instead of doing a to the 100th, I'm going to figure out my eigenvalues and eigenvectors. So I'm going to get, using the previous derivation that I did, c sub 1 times lambda sub 1 to the 100th times my u sub 1. Now that's where this lambda is an eigenvalue, and the u is the eigenvector corresponding to that eigenvalue. And then I know with this being a 2 by 2 system, I'm actually going to have 2 eigenvalues. So I need another part of this, c sub 2 lambda sub 2 to the 100th times u sub 2. And that again is where lambda sub 2 is the eigenvalue and u sub 2 is the eigenvector that corresponds. Now the derivation I did was for a 3 by 3, but it really could have been for any number. I could have done a 100 by 100 or 1,000 by 1,000 or anything for that matter. Okay, but this is a 2 by 2, so I'm going to leave this part here about the x sub 100 while I calculate the eigenvalues and eigenvectors. So the eigenvalues. If you remember to calculate eigenvalues, what I do is I set the determinant of a minus lambda I equal to 0. And that I was the identity matrix of an appropriate size, in this case a 2 by 2 identity matrix. And so if I do a minus lambda I, where a is this matrix up here, the 0.2, 0.4, 0.8, 0.6, I'm going to get 0.2 minus lambda, 0.4, 0.8, and 0.6 minus lambda. And I want to set that determinant equal to 0. All right, remember to do a 2 by 2 determinant. I do the diagonal, the main diagonal, 0.2 minus lambda times 0.6 minus lambda minus the secondary diagonal, which would be in this case 0.8 times 0.4. That's equal to 0. And that gives me 0.12, if I'm doing this out, minus 0.2 lambda minus 0.6 lambda plus lambda squared, and then minus my 0.8 times my 0.4, which is 0.32. I'm about to get a quadratic. I could either factor it or use the quadratic formula, but you'll find out it's actually not going to be too bad. Okay, if we keep in mind that little secret that I told you earlier about how I know one of my eigenvalues is always going to be 1 for a Markov chain, now not for any old matrix off the street, but for a Markov chain I know I'm always going to have 1, that's pretty much going to tell me that's going to factor into lambda minus 1 times something. Now I could actually work it out doing FOIL or whatever. Or you could use the quadratic formula like I mentioned before. But if you do this, can check to make sure this is really right. You'll see that this lambda squared minus 0.8 lambda minus 0.2 actually factors into lambda minus 1 times lambda plus 0.2. That gives me eigenvalues of 1, which we knew, and negative 0.2. Okay, so 2 by 2 matrix, I had 2 eigenvalues, not a big surprise there. Okay, I also need eigenvectors, right? Eigenvalues and eigenvectors. So I'm going to have to calculate my eigenvectors that correspond to each of these guys. So let's start with our lambda equal 1. Now remember, there are always infinitely many eigenvectors for every eigenvalue. Now the fact that I have eigenvector, singular, down here, just means I get to pick any of them. It doesn't really matter. They're all multiples of each other, so it doesn't matter, for example, if you have 1, 1, or if you put in 2, 2, or if you put in 5, 5, as long as you're consistent throughout the problem. Okay, so let's say I want the eigenvectors that correspond to lambda equals 1. Now if you remember, the way that I do that is I want to reduce a minus lambda I on the left and 0 on the right. So in this case, that's going to be my 0.2 minus lambda is actually going to be minus 1, and then 0.4. And then 0.8 on the bottom row, 0.6 minus lambda, in this case, that again was 1, zeros on the right. Okay, that turns into negative 0.8, 0.4, positive 0.8, negative 0.4, and zeros on the right. Now I'll save you all the pain and agony of it, but it actually is really quick and easy to reduce. That turns into just 1, negative 1/2, 0 across the top row, and then 0, 0, 0. So if I take this to reduced echelon form, row reduced echelon form, you know, my first step would be to get a 1 here, if you recall. And then once I get a 1 there, which you could divide by negative 0.8 to get, then I would want to get a 0 here. Okay, and that would also be pretty quick and easy. And it actually turns out that as soon as you get your 0 in this position, the whole row zeroes out. Not a big surprise, because I knew I was going to have infinitely many eigenvectors. This just gives me an equation now. It tells me that x sub 1 minus 1/2 x sub 2 equals 0. That tells me the relationship in the vector. X sub 1 is half of x sub 2. Now I could pick anything I wanted to. I'm just going to kind of write up that we're talking about x sub 1, x sub 2 is our vector. If I substitute in place of x sub 1, 1/2 of x sub 2, and in place of x sub 2, I write x sub 2, I can factor the x sub 2 out and get 1/2 in the top row, 1 in the bottom row, times any value x sub 2, except I wouldn't want to use a value of 0, because if you remember, 0, 0 is never an eigenvector. Okay, I can pick anything I want. I could pick 1/2 1. That would be fine. I could pick 1, 2. I could pick 5, 10. I could pick anything that's a multiple of 1, 2 other than 0, 0. Okay, so I'm just going to go with 1/2 1. Why not? That's what we got. Okay, now I need to find the eigenvectors that correspond to the other eigenvalue. So now let's use lambda is negative 0.2, and let's find its eigenvectors. Okay, so if lambda is negative 0.2, that's going to give me the a minus lambda I with zeros on the right of 0.4, 0.4, 0.8, 0.8, and then zeros. And you can see that one's also going to be pretty quick and easy to reduce, right? I need to get a 1 here. So I divide the top row by 0.4, yeah, which just gives me 1, 1, 0. And what do I get across the bottom? 0, 0, 0. So I knew that, again, I would have infinitely many eigenvectors. I knew I would get just an equation out of that. And that gives me x1 plus x2 is 0. Or in other words, that x1 is negative x sub 2. So my x sub 1, x sub 2 is negative x sub 2, positive x sub 2. Or in other words, just negative 1, 1 times any value that I want x sub 2 except for 0. Okay, so I can pick any vector that's a multiple of negative 1, positive 1 other than the 0 vector. I'm just going to go ahead and go with negative 1, 1. All right, so back to what we were doing here. I'm going to have to fill in for these eigenvalues. Now, if you remember, for lambda is 1, I wanted to use, I'm going to call that lambda sub 1 is 1. I wanted to use an eigenvector that corresponds, I'm going to use 1/2, 1. And then for my lambda sub 2, which was negative 0.2, I'm going to use u sub 2 to be negative 1, 1. Okay, so I've got my lambda values to go into this equation. I've got my u values to go into this equation. What's the one thing I'm missing? C sub 1 and C sub 2. I don't know them. Now, if you remember where they came from, C sub 1 and C sub 2 came from the initial state vector being written as a combination of my eigenvectors. Okay, so I want to be able to write my initial state vector, and my initial state vector in this problem was 600, 400 equals C sub 1, which I'm going to calculate, times my u sub 1, which was 1/2, 1, plus C sub 2 times my u2, which was negative 1, 1. Okay, if you remember how to multiply a constant by a vector, and then if you remember how to add vectors together, this just gives me equations. It essentially says 600 equals 1/2 C1 plus negative 1 times C2, in other words, minus C2. And then if I go along the bottom row, I get 400 is 1 times C1, which I'm just going to write as C1, plus 1 times C2, in other words, just C2. Okay, now you can solve those two equations any old way you want to. We could use a matrix like we did back in chapter 1. We could use algebra 1 type stuff. We could maybe substitute, solve for C1, plug into the other one, etc. Or if you happen to notice a negative C2 here and a positive C2 there. Do you remember your elimination method from good old algebra 1? If these guys have opposite signs, just add your two equations together. What do I get? Oops. So I'm just adding together those two equations. 600 plus 400 was 1,000. 1/2 of C1 plus another C1 is 3/2 of C1. And what happens with my C2s is that they're gone. So now if I solve for C1, I get that it is 2,000 divided by 3. I can then plug that number into either equation and solve for C2, I will get that C2 is negative 800 over 3. I'm finally ready to plug everything into this equation. So you're hoping that if we give you one of these questions, we're going to maybe give you parts of this, maybe give you the eigenvectors or give you the eigenvalues and the eigenvectors or something like that. But let's plug everything in finally to what we have. So our C sub 1 was 2000 over 3. That's going to go in here. Our C sub 2 was negative 800 over 3. That's going to go in there. Our lambda sub 1 was coming from, remember we got a 1 as our eigenvalue there. We figured out the eigenvector. We got the C sub 2. We figured out that our eigenvalue here was negative 0.2, and the U2 was the negative 1, 1. All right, let's fill it all in, finally. So x sub 100 is our C1, which was 2000 over 3, times my lambda sub 1, which was 1. 1 to the 100th is not that hard to calculate. You do not need a calculator. The eigenvector that corresponded to 1 was 1/2. 1 plus. Then I had this negative 800 thirds. That's times my lambda sub 2, which we figured out that was negative 0.2. That's going to be to the 100th power. And that's times its corresponding eigenvector. We were using negative 1, 1. Ready for the magic? It's the good stuff. What is negative 0.2 to the 100th power? Pretty darn small. In fact, a lot of calculators, you'll punch it in and it'll go 0. Okay, it's not exactly 0, but it's so darn close that it's just not going to contribute anything. The magic happens from the 1, because I know 1 to the 100th, 1 to basically the any power, is 1. So this stuff goes away. It contributes so little that it's just not worth mentioning. Everything boils down to this guy. And so if I work this out now, finally, I will have, now that we said that's just going to be 1, I'll have 2000 over 3 times 1/2. Well, that's just going to be 1000 over 3. And then 2000 over 3 times 1, that's about 333.33 and 666.67. So that was, which did we put on top? Clean and then dirty. So over time, if we continue with these habits, we'll have about 1/3 of our spoons clean and about 2/3 dirty. Probably not a good way to begin a restaurant shift. So let's take a look back at that second example we did. This was the one where we had birds flying all around from island X to island Y to island Z and back and forth. We had a transition matrix as given. We had our initial state vector, 400, 300, 800. And let's say that I gave you eigenvalues and corresponding eigenvectors for this situation. So if we had to calculate these on our own, obviously it would take a lot of space, but we could calculate our eigenvalues by setting the determinant of a minus lambda I equal to 0. And these are the numbers we would get, 1, negative 0.1, and negative 0.3. And then for each of these, we could calculate our corresponding eigenvectors. Now remember, there are infinitely many eigenvectors for every eigenvalue, but we just happen to choose these particular multiples of these eigenvectors. So for lambda 1 equal to 1, u sub 1 is 1, 1.25, 1. For lambda lambda sub 2 equal to negative 0.1, u sub 2 is negative 1, 0, 1. And for lambda 3 equal to negative 0.3, u sub 3 is 1, negative 2, 1. So let's say that I gave those to you. And I wanted you to calculate the steady state vector. And maybe we're just talking about after a specific amount of time, maybe after a year. Now, if you remember, our units of time in this problem were days. So after 1 year, we would be looking for x sub 365. But we also could just consider what would happen as n goes to infinity for x sub n. Okay, maybe you've done limits, maybe you haven't. But what I'm saying is, after a long period of time, we want to find out what x sub n is. All right, so if you remember our process, let's just say I'm doing the x sub 365. X sub 365 is going to equal c sub 1 times my lambda sub 1 to the 365 times my u sub 1 plus c sub 2 lambda sub 2 to the 365 times u sub 2 plus c sub 3 lambda sub 3 to the 365 times u sub 3. Now in each of these cases, the lambdas are the eigenvalues that were given. The u's are the eigenvectors that were given. And I've got to find these c's. Okay, that's my responsibility, is finding those c's. So let's say that I'm looking for the c's. The c's come from the fact that x sub 0 is c1u1 plus c2u2 plus c3u3. So in other words, my initial state vector which was 400, 300, 800, is equal to C1, which I'm going to find, times 1, 1.25, 1, plus C2, which I'm going to find, times negative 1, 0, 1, plus C3 times 1, negative 2, 1. That's going to give me 3 equations with 3 unknowns. My C1, C2, C3 are my unknowns. My equations are 400 equals, if I multiply this out, I get C sub 1, top row here I get minus C sub 2, and then plus C sub 3. Along the second row, I get 300 equals 1.25 C sub 1, no C sub 2's, minus 2 C sub 3's. And then the third row I get 800 equals C sub 1 plus C sub 2 plus C sub 3. Okay, that's going to give me an augmented matrix, if you're so inclined, of 1, negative 1, 1, 400 in the first row, 1.25, 0, negative 2, 300 in the second row, and then 1, 1, 1, 800 in the third row. In Chapter 1, we learned how to reduce that. Let's just say that I work it all the way out and I reduce it to row-reduced echelon form, and I get this matrix. So, I do all the normal steps that I would do. Get a 1 in the upper left. Yay, we have that. Below it, etc. So I go through all that stuff, and I get this. That means C sub 1 is 461.5385. C sub 2 is 200. And C sub 3 is 138.4615. All right, now I'm ready to fill that all in for my x sub 365. Okay, x sub 365 was C sub 1, which is 461.5385, times my lambda sub 1, which was 1, it's to the 365th, times the corresponding eigenvector, plus C sub 2, which is 200, times my lambda sub 2, which is negative 0.1. That's going to be to the 365th, times its corresponding eigenvector, negative 1, 0, 1, plus C sub 3, which is 138.4615, times my lambda sub 3, which was negative 0.3, to the 365, times the corresponding eigenvector, which was 1, negative 2, 1. Ready for the magic? All right, let's see. What's 1 to the 365th? Not very hard, right? Just 1. What about negative 0.1, though, to the 365th? Pretty much nothing, right? So this guy doesn't contribute enough to be mentioned. What about negative 0.3 to the 365th? Same deal, right? It's gone. Pretty much doesn't do anything. It all really boils down to the eigenvector and the C1 because that corresponded to 1, because everybody else is so small that when you raise it to 365th, it's gone. Now, I mentioned the 365th, but I also said something about as n goes to infinity. There's nothing magical about 365. We could say the steady state over an infinite period of time if we really wanted to. We just have to look at the fact that 1 to any power is going to be 1. So this part is just still going to be 1. All these other guys, if this is a huge number, are going to cancel out. So it's all still going to boil down to the constant that corresponded to the 1 and the eigenvector that corresponded to the 1. Okay, so now let's actually figure out what's going on with this system after a year. And these were birds on an island. So this x sub 365. If I multiply 461.5385 times 1, ooh, that's a hard one, I get 461.5385. Now that's on x. The next number that I get, I have to multiply the 461.5385 by 1.25, and I get 576.9231. And last but not least, I do it times a 1 again. So the second number was on y. The third number is on z. So you can see over time, now I know, again, we don't have 0.53, etc. of a bird, but maybe this is millions of birds. Who knows? Over time, this is going to kind of even out to where you have about an equal number on x and z, and then several more on y. Okay, so over a long period of time, that's what it's going to head toward. So there were two things that we talked about in this section. We talked about how to calculate x sub n for some small number n. And the way we did it was we took our transition matrix, we raised it to that power, and then we multiplied it by our initial state vector. The second thing that we did was we found the steady state vector. And remember, there were two steps to that. We had to first find the constants, however many eigenvectors you have. So we had to find x sub 0 is c1u1 plus c2u2 plus c3u3, etc., however many eigenvectors you have. And then we also found that for x sub n, we could do the c1 times the lambda 1 to the n u1, where that u1 corresponded to lambda 1, plus c2 lambda 2 to the n u sub 2 plus c3 lambda 3 to the n u sub 3 plus however many more you have. Okay, we had to find our own c's in this problem, and then we filled it all in. And we always had everybody going to 0 when you're talking about a huge amount of time, other than this one guy where your lambda was 1. So that's an introduction to Markov chains. Hope you found it interesting. Markov chains are powerful, and I hope you'll explore them a little bit more later.